Hey guys, Miss Amundsen here, and I hate technology. So my beautiful lesson that I had planned is not gonna work out. I've been trying to get it to work for 2 hours. So we're just gonna do a little old school today. Sorry, it's not really pretty. Can you label your notes? 9.3, we're gonna be talking about transformations. So a lot of this you might have seen last year in Algebra 2, but we're just gonna do a refresher and kind of practice a little bit deeper here for FST. So our goals for today: describe transformations to a parent function given the equation, and then the opposite, going the other way, writing the equation given a description. Before we get started here, technology, love it. Can you copy this chart into your notes? We're gonna fill this out as we look at some of the graphs to try and help us get a better understanding of transformations. So if you just hit pause real quick, copy that chart down, 10 rows, 3 columns. And you want this column for the general rule to be pretty big. So go ahead and pause, copy that in your notes. Okay. So when we are trying to describe transformations, these descriptions that we're going to come up with today will apply to any function that we're working with. So for this chart, just to explore, we're just working with the square root function. So the parent function, you could say, is square root of x right up there. But whatever we come up with for the general rule, that will also apply to any function, like the absolute value function, or x squared, a quadratic, any function under the sun. So let's start here. We can use our calculator to help us describe what's happening to the graph when we add some numbers to our equation. So if I look at just the graph of square root of x, what you want to focus on when we're describing the transformations is that vertex or that ending point. So as you can see right here, it looks like it starts at 0, 0, and then curves up this way. So that's our parent function. Now let's see what happens to that graph when I put a +3 at the end, outside that square root. So I can type it in my second line here, so see them both at one time. You should notice that it's the same shape of the graph, it's just been moved up. And if you were to count really closely, it's been moved up 3 points. So if I were to describe that transformation, I would say up 3. Let's take a look at the next one here. So it looks very similar, but now it's a minus on the outside, -2, oops, not that key. Check out the graph, that's the original. Here is our transformation. So if you look closely, it looks like that point has been moved down 2. Every point on the graph has just been translated down 2. That will also apply to other functions, like if I did x squared as my parent function, and then I did x squared +3. Oops. There's my original. Here's the transformed function. It's moved up 3. So what we can say in general, a general rule, for any function, we just call any function f of x, if I see the function has a number added to the end, we're just going to call that k, since we don't know what the number is. It can be any number. That means we are shifting our graph up that many units. Notice here is +3 on the outside, we moved up 3. So that will shift up k units, whatever k is. Then the second one, you might be able to figure that out. For whatever the function is, if I see a number subtracted outside the function, so after the function takes place, we're just subtracting 2 from all our y values. So if I see a number being subtracted outside the function, this is the function itself. I can describe that as down k units. All right, let's keep it going. Next two, notice the numbers that we have added to our parent function are now inside that square root. Pay attention to where that little roof of the square root ends. That's going to be important. If I graph those, so parent functions, oops, square root of x. You know what that looks like. Now graph square root of x plus 4. Notice my graph has moved to the left 4. Left 4. So then make your prediction. What's going to happen here? Minus 3 on the inside. Here's my original. It has moved to the right 3. So you may notice that it's opposite of what we would usually expect. Usually we would think a plus means to the right and a minus means to the left. But since we are plugging something in before the function takes place, it's kind of like we have to work backwards. Like, what would our value in here need to be to produce the same output? Well, it would need to be 4 less to produce the same output as the parent function. It's kind of complicated. As long as you know that anything that's happening inside our function is going to be opposite. It's going to be weird. So if I see a plus 4 on the inside, that really meant left 4. How we can write that in general is we say f of x plus a number. We'll use h. So this is just trying to say if you see a number has been added inside the function, it's no longer just f of x, it's f of x plus h. That means something's changed inside the function when we put it in the parentheses like that. So if I see a number added inside, that's going to move us left that many units. And then if I see a number subtracted on the inside, that would look like f of x minus h. A negative means right that many units. All right. Then the next two. So if you haven't noticed, they kind of go 2 at a time, have common rules. Next two, notice we have negatives. One is outside the square root, one is inside the square root. So looking back at our equations, think about what do you think is going to happen there. Okay, I have the negative on the outside, hit graph. There's my original. Here's my transformation. So you should notice that it kind of flipped. It reflected across the x-axis right there. So anytime you have a negative, it's going to have some sort of reflection. Negative outside means it's making all your y values negative. It's happening after the function takes place. So if I'm making all my y values negative, it's going to look like it flipped vertically up and down. So there's 2 ways we can describe that. We can say vertical reflection, which is what I like to say, or reflection across the x-axis. Then if we did the negative on the inside, see what it does there, make your little prediction. There's our original. And there is our transformation. Notice it has been reflected from here over here. It's been reflected across that y-axis, or you could say it's been reflected horizontally, side to side. So horizontal reflection or a reflection across the y-axis. So then to write our general rules, this is saying have a negative in front of the whole function. So to write that in a general notation, function notation, we write negative f of x If I just threw a negative in front of the whole function, that's going to be a vertical reflection. Or across the x-axis. If we're reflecting up and down, you're crossing the x. Then the next one, we would say f of negative x. That's just trying to tell us if I see a negative in front of the x inside the function. Inside the parentheses represents inside the function. If I see the negative there inside, then that's going to be a horizontal reflection. Okay, then the next four get a little hard to recognize on a graph. So for some of these, you're just going to need to trust me when I tell you the rule. But if we look at this one here, it has a 5 in front, and remember that is being multiplied if I don't see any other symbols in between, 5 times square root of x. So that's saying take your original function square root of x and then multiply all your outputs by 5. Your outputs are your y values, so it's going to make your y values 5 times bigger. If I look at the graph, my original here, notice it stretched vertically. It's like I took that line and pulled it up this way. Our y values are 5 times bigger, so it's going to shoot up a lot faster. So how we would describe that, we would say it's stretched vertically, so vertical stretch. And then sometimes you might be asked to say, what is that stretch factor, by how many? So it's been stretched 5 times as big, so I would say vertical stretch of 5. Then next one, notice we have a 1/2 in front. It can be 0.5. If I look at that graph, there's my original. There's my transformation. It's been shrunk down. It's been compressed, pushed down vertically. It was up here and then we smushed it. So when we see a number like that, that is going to be a vertical compression. And we can say of a factor of 1/2. Everything's going to be half as big. So in general, if I see a number being multiplied in front of the function, that's going to be a vertical stretch of however many. So how we can write that for our general rule is any number, we'll call it a, times the whole function is going to represent a vertical stretch. And then any number again times the function will be a vertical compression. But let's talk, how can I distinguish between the two, stretch versus compression? If I'm multiplying everything 5 times, that's going to make it a lot bigger. So if this number here in front is greater than 1, so if a is greater than 1, it is going to be a stretch. And then for the compression, if that number in front, now the shortcut way is to say less than 1, but technically it has to be positive for a stretch or compression. So we say, if this number is between 0 or 1, then it's going to represent a compression. So we can write, if our a value is between 1 and 0, write it like that. In general, you just look and see, is it less than 1? Because when you get to negatives, those are going to be treated separately. You'll see. Okay. Then the next two are pretty crazy. The horizontal stretches and compressions are kind of hard to see, and they're weird. Everything on the inside is weird. It's opposite of what we would expect. So if I were to graph this with a 3 inside, there's my original. There's my transformation. It's really hard to picture in here, but what's actually happening is this original is being shrunk this way, pushed together. And when that happens, it makes it look a little bit taller. But it's hard to see really on a calculator that it's been shrunk. It's hard to tell the difference between shrunk this way versus stretched vertically. So that's why we really need to be able to know based on an equation what's happening. And so if we see a number inside the function being multiplied, that is still going to be a stretch or compression, but it's inside now, so it's horizontal. So that's going to be a horizontal compression. And then if I have a number in front being multiplied inside the function, and that number is less than 1, or between 0 and 1, we would say horizontal stretch. Told you it's going to be weird. The inside stuff is weird. So a big number or a number greater than 1 means compression when it's inside, and a number less than 1 means stretch when it's inside. So it's the opposite. So we can say for our general rule, if I see a number being multiplied inside, we'll call that b, being multiplied by the x, then it's going to be a horizontal compression if that b value is big. So if that b value is greater than 1, it is going to be a compression. If that b value is less than 1, it will be a stretch. So we can say f of b times x again will represent a stretch if that number inside is less than 1, or technically between 0 and 1. So we're done with our chart. Take a second to continue filling that out. Pause the video if you need, and then we will move on to just a couple more notes, kind of bringing it all together. So pause, copy that down. Okay, then let's write some even more general rules. So kind of bringing this all together, here's everything that you need to be able to handle for this section. We're going to ask you about shifts, that's like translations, left, right, up or down, reflections, and stretches or compressions. So this chart breaks it apart one change at a time. Notice here, okay, we had a number added or subtracted outside the function that moved us up or down. Up and down, that's a vertical movement. When I had a negative outside the function, that moved us vertically as well. It was a reflection. And then when I had a number being multiplied outside the function in front, that was a vertical stretch or a vertical compression. So you should start to notice that anything happening outside your function is a vertical change. Anything happening inside your function is a horizontal change, and it's annoying because a plus really means left, a minus really means right. A big number really means compression, and a small number really means stretch. So those are the things that get kind of weird, but you guys get to use your notes, so I would write this down so you have all the rules, you don't forget. Pause real quick. And then we have one more page, kind of bring it all together before I let you go for practice here. So in general, and when I originally made this lesson, this had beautiful color coding and it was very nice, but obviously you can't see that right now. In general, these are all the possible changes that can happen to a function. And what I want you to notice, first of all, this f and these parentheses and this x are just coming from here. It's just saying if I had some function f of x, and I added a number inside, what would happen? Added a number outside, what would happen? Multiply a number in front of the function, what happens? Multiply a number inside the function, what happens? So some people like to put them all together at one time like this, just to straighten out in your brain all the possibilities. So I'm going to run through and just label these, and then that will be it for our notes. So negatives, anytime you see a negative in front, that is going to represent a reflection. If it is outside the function, so like here, it's outside the square root function, then I would say that represents a vertical reflection, or reflection across the x-axis. Then a number being multiplied in front could be a 3, it could be a 5, it could be a 1/2, it could be a 2. That is going to represent a vertical stretch if it is greater than 1, or a compression if it's less than 1, or between 0 and 1. The reason this is important to say that it has to be greater than 0 is because we don't want you to think that this represents a stretch of -2. That doesn't make sense. You can't stretch something negative twice as big. So when you see a negative paired with a number being multiplied, you treat those separately. This would represent a vertical reflection, and the number itself would represent the stretch or compression. So in this case, a vertical stretch of 2, because that number was greater than 1. All right, keeping it moving. This F parentheses are just saying function notation, so we don't need to label anything there. F is not a variable in this case. Negative inside the function will also represent a reflection, but if it's inside the parentheses, inside the function, it is going to be a horizontal reflection instead of vertical. Then, I'm running out of colors. A number being multiplied inside the function. I have to draw it up here. This one needs a little explanation. So that number being multiplied inside the function is still a stretch or compression, but since it's inside the function, it's horizontal. And we would say stretch if your B value is less than 1, opposite. Okay, or between 0 and 1, sorry, we should say. Or compression if your B value is greater than 1. And the weirdest thing here is if I ask you what's that factor, like stretched by a factor of 3 or compressed by a factor of 1/2. To figure out the factor that you're stretching or compressing by, you are going to take B and find the reciprocal. So find reciprocal, which remember just means the fraction flipped of that number there to determine stretch or compression. To determine stretch or compression factor. So like, for example, down here, this negative means a reflection. It's inside the function, inside the square root, so that's going to be a horizontal reflection. And then this 3 separately, that's going to represent a horizontal stretch or compression. So if I look at the number 3, following my rules, it's greater than 1, which means it's going to be a compression. So I'll say horizontal compression. But then if I ask you of how many, of what factor, you would say 1/3. It's weird, you gotta flip it. Then the next 2 should be a little bit easier. I just think those are easier because it's just added or subtracted after the x. So if you see a number being added or subtracted, it's going to be just a shift. We're just shifting